PDO, on which the ENSO cycles are superimposed. Their interaction can amplify or dampen rainfall in the country. Note that the PDO shift in the mid-70s matched the timing of shift of ENSO state from La Nina dominance to El Nino dominance. There are other longer climate cycles that influence precipitation, but available instrumental records are too short or too patchy. To examine the signals and influence of these longer cycles, we need to extend the available records. To do this, we can utilize historical and geological records. For example, Vaquero and others in 2005 identified an El Nino event in Manila in 1864. They used the meteorological observations of a Spanish friar named Antonio Llanos, who published his work in a Spanish scientific journal. In this figure, a comparison is made in the reconstructed precipitation for 1864 and average precipitation from other time periods. Another source of climate information is the geologic record. Shown is an X-ray of a Porites coral skeleton. The skeleton of corals is one example of geologic material that can be used for paleoclimate reconstructions. Corals can be age-dated, and their annual growth bands, comprised of a pair of light and dark bands, can be used to count the exact number of years of record. The growth of Porites is within 1 centimeter per year. Thus, a 1 meter long sample can yield a record of about 100 years. Rose Berdin, who did her MS work here in UP Diliman, sampled living and fossil corals in Samar and used stable oxygen isotopes to deduce changes in precipitation for her dissertation at the Australian National University. Shown in the table are the duration of dry years caused by El Nino and other events. The living coral indicates that the longest drought in the immediate past lasted for 3 years. This is consistent with instrumental records. The period at 5.8 thousand years ago showed the longest reconstructed dry event, which lasted for 10 years. Given this information, it is prudent to have a management plan that can address at least 3 years of drought, and best if it can address a 10-year long drought. Other geologic materials, such as lake sediments, can provide more continuous records, but their resolutions are much coarser. Peter Zamora, another former MS student of UP Diliman, in his thesis, used the dry bulk density of Laguna de Bay sediments as proxy for decadal to multi-decadal average precipitation. An increase in dry bulk density is associated with an increase in average precipitation and vice versa. The segment in green, which roughly corresponds to the past 100 years, is offset to lower bulk densities because of faster sedimentation due to human activities. But the trends within the segment are consistent with PDO trends. The overall trend is consistent with similar reconstructions from Taiwan and Borneo. The proxy record indicates a wetter than present condition about 1,000 to 1,500 years ago. Furthermore, a drier than present condition may have occurred between 650 to 900 years ago. Cycles from the record yielded dominant periods of 842 and 145 years, and other minor periods shown in the slide. These frequencies are within identified sun cycles from radiocarbon production reconstruction. A 1,500-year cycle, commonly found in longer paleoclimate records elsewhere, can also be inferred from the overall trend. Recombining the dominant cycles yields the curve in red. If one is to extend the cycles into the near future, we get that trend. So, instrumental, historical, and geological records tell us that there is natural variability in precipitation. We've had rainfall events that can last for just a few hours and exceed the monthly rainfall normal. We've had multi-decadal average precipitations that were higher or lower than present. And we've had droughts that persisted by as much as 10 years. They give us some ideas of what is in store for us with the ever-changing rainfall. But we need to study the records further so we can improve our understanding of this variability. Other countries have developed technologies and systems that allow them to predict long-term and short-term changes. They have technologies and systems that allow them to monitor events. Let us use what we can, like the multivariate ENSO index and TRMM, so they can help us prepare for incoming events. But we also need to install additional rain gauges upstream of population centers for use in flood forecasting. And let us hope that Pagasa's Doppler radars will be in place very soon. Other actions can be implemented to lessen the impact of rainfall variability. The next two presentations will tackle this in greater detail, but we would like to share two thoughts. The first is based on the relationship that recharge increases with increasing forest cover. The numbers in the figure represent Philippine regions. This relationship tells us that aggressive reforestation can protect our groundwater resources. But even if we are able to improve recharge, we should still set aside groundwater as our water source during emergencies or crises such as droughts. Sadly, at the pace we are extracting groundwater, we have greatly lowered the water level, induced saltwater intrusion, and introduced other contaminants to our aquifers. It will take decades or even more for this to recover. The second thought, and this is my last slide, is the use of different and complementary water impoundments. We were reminded recently by Antonio Oposa of Republic Act 6716 passed in 1989, which requires every barangay to have a rainwater catchment system. An example of a catchment system already in use in the country is the small water impoundment or sweep shown by these photos taken in Bohol. In areas frequently impacted by droughts, sweeps can extend the availability of water for agricultural and other household needs, thus extending the viability of crops. These sweeps can also serve as flood control structures, and they can also contribute to recharge. Maraming salamat po. Okay, the next presentation for the Food Security Group will be given by Ino Lansigan. Ino.
Thank you very much, Ando. Let me first introduce the members of our team, led by our team leader, Dean Diz Cabrido of UP-SERP. We also have our Dean Vicky Espaldon of UPLB CESAM. Also Dean Oscar Zamora of UPLB College of Agriculture. We have Professor Rene Vega and Professor Cesar Sevilla watching in UPLB. Hello. We have also Dr. Gigi Culadilla of UPLB CESAM. We have Dr. Rogers Concepcion of UPLB CESAM. And yours truly. As Professor Ando Siringan discussed earlier, the Philippines, with a population of more than 90 million people, faces threats from climate variability. This is in the form of tropical cyclones, floods and droughts, drastic changes in rainfall patterns, sea level rise, and even increasing temperature. Climate-related hazards are also threats to crop production and to water supply for agriculture and other uses. The impact of extreme climate variability on crop production is very evident in the impacts of El Niño events of 1997-98 and also 1982-83 on rice production in the Philippines. These events have brought significant crop losses worth billions of pesos on rice and corn alone. The decrease in corn production will result to increased farm gate prices, which could consequently increase the price of feeds and hence the prices of swine and poultry. Changing rainfall pattern together with land use changes have also significantly altered the hydrology of crop production areas and have distorted the dependability of water supply in many regions. In recent years, there are now local observational evidences in the Philippines of variable rainfall patterns. During the last decades, the occurrence and distribution of annual maximum daily rainfall events, the number of wet and dry days, and the minimum and maximum daily temperature have changed. These changes have significant impacts on crop production. Understanding the effects and impacts of climate variability on agriculture and on the dependability of water supply is critical in formulating strategies and adaptation options to minimize the adverse consequences. Appreciable increase of half to 1 degree Celsius in the annual minimum daily temperature in some locations in the Philippines, like for example in Los Baños, has resulted to decreased rice yield. Weather and climate are important factors in crop production. Recent studies have shown that a 1 degree increase in temperature will result to about 8 to 14% loss in rice yields during the dry season. And similarly, warming by half to 1.5 degrees Celsius could decrease corn yield potential by about 2 to 5%. It should be noted that temperature increase of 1 degree Celsius is no longer a scenario. Based on available historical weather data, it is a reality. Variability in rainfall patterns has also triggered the emergence of new pests of crops and also affected livestock growth and development. For livestock, for example, increase in temperature and humidity significantly reduce feed intake and body energy reserve, and consequently, growth and reproductive performance. For example, in swine, the number of pigs produced per sow will be reduced by 26% from 19 to 14 pigs per annum. Drastic changes in climate variability has altered the hydrologic regimes in critical watersheds, which provide water for irrigation, power generation, domestic, municipal, and industrial uses. This is further exacerbated by the rapid population growth, adding increased pressure, leading to water stress. These events have affected much the dependability of water supply, not only for agriculture, but also for other uses. Recent studies show that regions with fast-growing populations will likely experience varying degrees of water stress due to increasing water demand. These situations may result to competition and conflict on water uses. How do we then respond amidst these changing rainfall patterns and climate variability? What are the challenges, information and knowledge gaps? There are now a number of field-tested crop production technologies and strategies that may be applied. These include the following. First, adjusting the cropping calendar. Planting of crop is synchronized with a period with more dependable rainfall. And by considering the water requirements of crops at different stages of growth and development, a dynamic cropping calendar can be determined based on estimated or projected crop yields, given the seasonal climate outlook or forecast for the cropping season. Modifying the cropping system, crop combination, or crop rotation. This involves decision on what crops will be planted, considering the seasonal climate forecast for the growing season. There are crops that require less water, which can still make use of available soil moisture content to give reasonable yield levels. Crops that are known to be efficient in their water use are sorghum, sweet pepper, ube, winged bean, pigeon pea, fall sitaw, ginger, cassava, asparagus, black pepper, sweet potato, mung beans, cucumber, coffee, and peanut, and many more. Planting of these crops with short crop duration is the most efficient means of drought escape and the most effective strategy of crops under low moisture conditions.